Okay, thanks very much. Welcome, everybody. Good morning. It's really wonderful to be in this incredibly beautiful place at this wonderful time with France in the finals. Okay. Uh, and so I'm going to talk to you about what, in particular, the LIGO and Virgo collaborations do to look for signals in the LIGO data. And it's a challenge, and so there's a lot of details, and I'll go through as much as I can. I should say that I was extremely impressed with all the talks that were given yesterday afternoon. And when I was preparing these slides, I usually do it, well, I have to make some assumptions, just what's the level of the audience. I underestimated the level of the audience dramatically. So there may be plenty of slides and plenty of parts of the discussion that are pretty, all this stuff. On the other hand, I imagine that there is a broad range of people in the room, and there may be some people who don't. So it might still be worth talking in some detail about some of the finer points. And in particular, for example, I'll spend some time talking about software. I'll spend some time talking about the waveforms and how important they are, and how we produce them and make them available to you, for example. And uh, and you may have seen all this before, or you may learn something. In any case, the other thing is that since this is a summer school, I assume that schools have homework, right? And so I'm going to give you lots of homework. And when I first arrived and I asked around, and people said, "Oh, we're not getting really any homework," but then came Stefan, and he gave you homework, and it looked like a lot of fun. And so hopefully, well, I don't know. We'll see whether the homework that I will give you is anywhere near as fun. But when it comes to software, it's often the case that you're handed a large piece of software and you go, okay, learn something, run it. And you do learn something by running it. You don't always get a lot of insight unless you do it for a long time. And so I'm going to try to help build up the insight into what all the software does. And then probably on Friday, we will go through some exercises with the actual software that the LIGO Virgo scientific collaboration uses to analyze the data. Okay? Good. And I am representing the LIGO Virgo collaboration in this talk. So one thing I won't be able to do is defend other approaches to analyzing the data. We sort of think that our approach is good, but it's not the only way to do it. Okay. Good. So first, the statement of the problem, exactly what it is and why it's kind of hard to do. We're looking for weak signals in noisy data. If you haven't already experienced this, when you look at the LIGO data as is, you're not going to see any signals in it. You have to dig deep to find signals. And in particular, the signals are often, if you plot the data on a time series, strain H of t, we call it, then if a signal is in there, it's going to be buried in the noise at first. So it takes some effort to find these things and to find them with confidence. The first advanced LIGO observing run lasted 5 months, let's say around 10 to the 7 seconds, and 3 events were found. And these events were all high mass binary black hole systems, relatively high mass binary black hole systems, and they last fraction of a second in the LIGO band. And the LIGO band, depending where it starts, is a matter of, well, where the noise curve is. But in O1, let's say it started around 30 hertz. If you were to look, this plot isn't exactly addressing the question, but a little bit. But if you look at the time, it happens to be in minutes, of a signal, a compact binary signal in the LIGO band versus the total mass, you see that, of course, as the mass goes up, the merger happens at a lower frequency, less time is spent in the LIGO band, and depends on where the band starts. So there are curves, green curves for starting at 40 hertz, and red and blue curves starting at 15 and 10 hertz respectively. This is equal mass systems, and for binary black holes, you see that well, our first detection, GW150914, was about 65 solar masses, and the analysis started between 40 and 15 hertz. It was about 30 hertz, and you can see that we're talking about, well, a fraction of a second in the LIGO band. You can calculate these curves using this formula, which we can actually derive pretty easily. This is the chirp time, which is often called tau zero in the literature, and it's given by this expression. You can see it goes like the mass of the system to the minus fourth power, and in the denominator there is the initial separation of the two black holes, which is related to the frequency at which they're orbiting each other, the orbital frequency, by Kepler's laws. You can also see a 1 over the symmetric mass ratio, which if you don't recognize, I'll talk about the symmetric mass ratio a little bit later. So you can see that for equal mass systems where eta is 1/4, that's the shortest time in band. And when systems are unequal in mass, eta is smaller than that, and the chirp time is longer than that. Okay, so unequal mass systems spend more time in the LIGO band, but they actually have less power, and so they typically have less signal-to-noise ratio, even though they spend more time in the band. Okay, back to the statement of the problem. So that means that all but about 10 to the minus 7 of the data contain nothing but noise. Now you should be laughing at me for that. That's an outrageous statement to make because, of course, the data actually contain loads and loads of undetectably low signal-to-noise ratio signals from the distant universe, which you can potentially detect through other methods like the stochastic methods that we heard about last afternoon. So the CBC search pipelines have to find the 10 to the minus 7th of the data containing a detectable signal. That's the needle in the haystack kind of a problem. Now the detectors are, of course, expensive. We've invested on the order of $1 billion and on the order of countless person years of effort to build the detectors. So you can't skimp on the software. You can't say, oh, we'll just take shortcuts. We don't have to do things as perfectly as possible. You have to work as hard as you possibly can to get every little bit of information out of the detector. Otherwise, our instrument science colleagues who devoted their lives to deliver this fantastic detector to you will be furious at you. So you don't mess around. Now it's been shown that if a suitably precise model of the signals of interest exist, then matched filtering, which we'll talk more about, which you already know a little bit about if you don't know a lot, using the models as templates is, quote, optimal, unquote, for identifying weak signals in Gaussian noise. And that's been documented in this classic textbook, Extraction of Signals from Noise by Weinstein and Zubikov, and that was already 50 years ago. Optimal means that you can come up with other methods, but they won't ever be as good. Okay? Now that's for Gaussian noise. Gaussian noise means random fluctuations and never going more than 2 or 3 or 4 sigma beyond the mean, which would be 0 for detrended data. But LIGO data are not Gaussian. LIGO data are neither have strong non-Gaussian fluctuations. We typically call them glitches, but there's a whole menagerie of different ways in which they can fluctuate way beyond Gaussian limits. And they're also non-stationary. It's changing with time in a variety of ways. And that's what makes this problem less than optimal and less than routine. That's what makes it challenging. So I'll have to spend some time about how we deal with non-Gaussian, non-stationary data that could easily screw us up if we didn't put a lot of effort into it. This is true not just for a single type of signal with one model, but of course our signals, like compact binary coalescence, depend on parameters. Okay, and those parameters are unknown. We know the range at which they can appear, masses and spins in particular, but we don't know what value is going to, for those masses and spins, is going to correspond to the next signal that we observe, of course. And so we build not one template, but a bank of templates, and that corresponds. And in the second observing run, I'm talking about 600,000 templates. Okay, so quite a lot. And you might argue that this optimal argument is not appropriate when you have more than one model, when you have many models. Turns out that it's also true. It's true even if there are unknown model parameters, like masses and spins, so that we have many, many templates, hundreds of thousands of them. And even then, that means you have a trials factor. Each template gives you new opportunities for fluctuations, non-Gaussian or even Gaussian fluctuations in the data could ring up, we say, ring up a template. That is past the template filtering process, match filtering process. So that's a trial. And if you have 100,000 templates, that's 100,000 chances, 100,000 trials for a noise fluctuation to fake a signal. We deal with this all the time. It means that we have to put a threshold on the output of the match filter that's higher and higher and higher. But as we'll see, you still win. You still win by doing this. But you only win if the templates are accurate, and they have to be accurate over potentially very many wavelengths. Because what the templates are doing is looking for constructive interference between oscillations in the data and oscillations in the template. And if the signal has, say, 100 oscillations, and the template isn't precisely in phase for all 100 of those, let's say it falls pi out of phase halfway through, you will get constructive interference for the first half and destructive interference for the second half, and you will get much, much less of a signal. You have to have a template whose every oscillation is accurate all the way through the LIGO band, and produce much less than, a fraction of pi of a phase shift with respect to what the real signal is in band. And you see that we've got a bit of a chicken and egg problem. If we don't understand the physics extremely well, we'll get those templates wrong. We won't find the signals. We'll never find out that we got the signal wrong, the physics wrong. Okay. Oh, I'm sorry.
And these models are currently relevant for non-eccentric mergers?
That's right. We will be talking about the kinds of parameters that we'll limit ourselves to, and we're going to limit ourselves currently to circular or quasi-circular binaries. We're going to ignore eccentric ones. That's a bias. It's a dangerous one. So you got to test that. And I'll talk about what motivates us to do that, at least in the initial round. Okay? Yeah. Oh, I'm sorry. Forgive me. Whenever I use an acronym that is unfamiliar, please speak up. So CBC is our jargon for compact binary coalescence. Okay? Now we used to call these inspirals until we realized that, if in the old days, again, I've been in LIGO for many, many years, in the old days, our targets were binary neutron stars. Okay? Not high mass binary black holes, because we really didn't think there were going to be that many high mass binary black holes. Well, of course, we were just guessing. Okay? A lot of time was spent on understanding the in-spiral phase, because for low mass systems, you can spend a lot of time in the LIGO band with many, many oscillations, so you got to get that as right as possible. Okay, so we called them in-spirals. Then we realized, oh my gosh, well, I'm whitewashing the history. Oh my gosh, we might indeed find binary black holes, and in that case, they'll merge within the LIGO band. And so there'll be not just the in-spiral, but also the merger and the ring down. And until about 5 or 6 years ago, we did not have good waveform templates for in-spiral merger and ring down. Now we do, and it took quite a lot of effort. And it's really been only in the last 5-7 years that we've been able to do that. Okay? And especially including spin. Tremendous amount of progress in the last 5 to 10 years developing these waveforms, or waveform families, as we will see. And so our mindset was on in-spirals. We call that's the group that was convened to write software to search for these things was called the in-spiral group. And then we realized, in-spiral merger, ring down, they're all equally important. We have those waveforms. We need one word for it, and that word, somebody came up with the word coalescence. Compact binary coalescence. Of course, they're binaries, and you know why they need to be compact, right? Because non-compact ordinary stars have radii of millions of kilometers, and they will start touching each other when they orbit, when by Kepler's laws, they're orbiting each other at very, very low frequencies, way below the LIGO band. We cannot see ordinary stars merging. We can only see the compact ones. They're much, much smaller, neutron stars and black holes. They can get much closer together by Kepler's laws. They're orbiting much faster. And indeed, orbital frequencies on the order of 10 hertz and higher corresponding to gravitational waves on the order of 20 hertz and higher corresponds to an incredibly extreme system, right? These things are moving close to the speed of light. The mass of the sun, the size of Geneva, and orbiting each other at close to the speed of light. These are unbelievably extreme systems. So it's important that those templates be as right as possible. And it's less important for higher mass systems. They spend less time in band and fewer cycles in band. And because they spend fewer cycles in band, you don't have to get those cycles precisely right. And in fact, as we approach higher and higher masses, like IMBH, intermediate mass black holes on the order of 100 solar masses or higher, you're talking about a handful of cycles in the LIGO band. You don't even need match filtering at that point. You can use burst techniques like what we'll learn about from Marianne later today. I think it's later today? Right, okay. Good. Tomorrow, okay, whatever. All right, so I will talk about the techniques, and then I'll talk a little bit about the search pipelines, software that reads in the data in quasi-real time, within seconds of a gravitational wave passing through the LIGO and Virgo detectors. The data are collected at a central place, usually Caltech, but also in Kashina, and run through these pipelines, these software pipelines, and we can identify the presence of a signal within, well, in O2, many 10 minutes, but in our third observing run, which we hope will start next January, we're aiming for sub-minute latencies. Okay, so all this is done in quasi-real time. Okay, and these detection pipelines have funny names, as usual. PyCBC, which means that most of the code is written in Python. GST-LAL, I'll talk more about that. That's GStreamer LIGO Algorithm Library. Okay, all these silly acronyms will, if you remind me, will get spelled out. This one is the multi-band template analysis, and this one is the, oh my gosh, IIR stands for infinite impulse response filter. SP, I don't remember even what it stands for. Okay. But the two workhorses are PyCBC and GST-LAL, and they were both used for detecting all of our events in O1 and O2. All right, and I'll talk much more about them. But let me just, that's the sort of statement of the problem. And in a nutshell, we have the two approaches that I've mentioned so far for looking for transient signals in LIGO data analysis. We have the template search template, the template searches, which are based on as precise as possible templates, many, many of them, each one, if you like, is a puzzle piece that can be assembled together to understand binary black holes in the universe. And burst searches, which don't use templates per se, although there are variations of it, and which look for short signals, maybe sometimes as long as seconds, in the LIGO data that produce excess power above the noise. And that's a bit of a challenge because the noise fluctuates all the time due to the non-stationarity of the detectors. So there are two other kinds of searches that you'll be hearing about, stochastic and continuous waves. Those are different, and they take very different analysis techniques. So one of the very fun things about being in this field is that we do have many different kinds of morphologies of signals. Broadband, narrowband, short duration, long duration, and they all require different techniques to do searches optimally. And so they're actually, it's actually a sort of a very broad and interesting range of techniques that you get to learn about. That's what makes it fun. There's also the question always in the back of our minds. When we're looking for the unknown, we don't know necessarily what the morphology of the signal in time and frequency is. Are we covering all of our bases or not? Are there holes in our range of morphologies that we search for in the LIGO data? And that's an outstanding and interesting question. Okay? And one of the most interesting holes that has been around for a long time and that is now being closed is that for burst-type searches, short transient searches, they used to be optimized for signals that were significantly less than 1 second long. But you can imagine signals, for example, a neutron star being excited in a maybe because it's just been formed in a merger, and producing some quasi-stable thing like a hypermassive neutron star that's highly perturbed when it's born, shaking like crazy, and potentially, depending upon the model of the neutron star that you believe in, shaking for potentially many, many seconds or even minutes. And then you can imagine other kinds of sources that could be transient but lasting minutes without models that we have, without precise models for how they shake. And then you've got a very large parameter space in terms of duration and spectrum, frequency spectrum that you're looking for. And those kinds of long duration transients were not being covered until recently. And I'm sure Marianne will tell you a lot more about that later on. But I'm going to focus on the one that we think we understand the best. It's often said that CBCs, compact binary coalescence, are the, people often say they're the most likely sources, and it turns out they were the first ones that we observed. But I don't know if they're the most likely sources. And I could argue that any of our different morphologies could be found next. Well, we'll see. Okay, so let me start with the basics. And this is so basic that it might be that it's trivial for you, but it might be that you'll learn something, especially if you have never done much in the way of numerical studies, analysis of, basic astronomical things like compact binary orbits. So let's remind ourselves a little bit about relativistic orbits, because you're going to need this for the homework that I give you. Okay, so we'll be talking about the in-spiral phase, not the merger phase, and we can approximate the orbit as quasi-Keplerian, even though it's relativistic already at this point. Kepler's laws, as we saw from Tom's talk yesterday, are still valid until you get to very high, until you get to really relativistic velocities. So let's talk about it as being quasi-Keplerian. It's not, of course, Keplerian. There's energy loss due to gravitational wave emission, but we're going to assume that it's small enough that the orbits nearly close on themselves. So the in-spiral is slow. Okay? So that's what we usually call the adiabatic approximation. We'll also assume that the orbit is quasi-circular, and I'll ask you why we tend to make that assumption. Because what?
Well, one, it's easier to do it mathematically, and two, also if they've been orbiting each other for a long period of time, they radiate enough energy away in order to create circular orbits.
That's right. That's the real reason is that if the stars have if the binary has formed in the usual way that we think binaries form, which is through common evolution. That is, those two stars have been together for millions and millions of years, even before they went supernova and turned into neutron stars or black holes. If they've been orbiting for a long time, any initial eccentricity gets radiated away in gravitational waves. And that happens for pretty obvious reasons. So here's one star, here's another star orbiting in an elliptical Keplerian orbit, and this is periastron over here. And as we swing by periastron, you can see the acceleration is higher, and that means that as the secondary star orbits around over here, it's going to feel more acceleration and emit more gravitational waves in a burst. Usually pretty beamed, actually, relatively speaking, a burst of gravitational waves. Only here, much less so here, much less so here, much less so here. This is very much analogous to electrons in a magnetic field radiating bremsstrahlung. So if you're unfamiliar with the term. Which is radiation from acceleration. And that happens in gravitational waves as well as electromagnetic. And this will serve to preferentially circularize the orbit. And this happens actually pretty quickly, such that if these things have been orbiting each other, not for millions of years, but for at least 20 minutes, already by the time it gets into the LIGO band, it's been circularized. By contrast, it's possible to imagine here's a black hole, and here's another black hole that's not bound to it at all. but we're in a dense stellar environment. Or maybe there's another little black hole orbiting this guy, and a bigger black hole goes by and swings by and kicks this guy out and gets captured into a highly elliptical orbit that's already in the LIGO band. That is to say, orbiting very, very quickly. We call that a hard orbit. Okay, so it's gotten into a very hard orbit, and it's highly elliptical. And it's so the an elliptical orbit we might find such systems, and it'll tell us that these systems were formed either in dense stellar environments rather than in sort of common evolution over millions of years. Or maybe there's it's a three-body type problem, so maybe it's a triple, and you're getting very interesting, complicated orbital dynamics between the three stars that produce a tight binary. So that can happen, and that would be really interesting to see. So we do want to look for these kinds of things. Even there, of course, they're rare. Especially they're rare because this kind of capture through bremsstrahlung, it's a capture through bremsstrahlung. It swings by, either kicks this out or emits a strong burst of radiation. Either way, loses enough energy to become bound. Okay? And when that kind of thing happens, it still will circularize within a few cycles. And so we still might be able to catch it, even with circular templates. Does that make sense? I'm not, what I just said is not, of course, 100% true. We could miss it. It could stay eccentric because of its properties for longer than what I implied. So this is still an outstanding issue. Yeah.
Sorry, another question. With highly active galactic nuclei, isn't there more? So we said that it's quite rare to have black holes in such elliptic orbits. But if we have a lot of fast-moving black holes and galactic nuclei, then we'd actually have quite a few of them, right?
That's right. That's right. However, so this distance over here, let's call this the impact parameter of the original wandering star. In order to get into a very tight, I mean, LIGO orbits are very tight. These things start orbiting each other 10 times a second. Okay, you need an impact parameter that's very, very small. That corresponds to a cross section that's very small. The cross section for producing eccentric orbits through this kind of capture in the LIGO band is tiny. It's much more likely that these things form at larger cross section. And when they form at larger cross section, by the time they get into the LIGO band with a tight orbit, they've circularized. Okay? So it's about probabilities. It's about probabilities. Good. Okay. So we can then use the non-relativistic Kepler's third law to develop some intuition about these things. And you'll recall that Kepler's third law relates the orbital period, the orbital frequency. This is the angular orbital frequency, 2 pi times the frequency in hertz times the orbital separation. Relative orbital separation to the cube power is the total mass. Okay, and that means the orbital frequency. The orbital frequency is 2 pi times the orbital. The angular orbital frequency is 2 pi times the regular old. Is there a word for it? Orbital frequency, and that's pi times the gravitational wave frequency. Here is the Newtonian kinetic energy and potential energy. This is the velocity of the system. The velocity of the system, of course, the orbital angular orbital frequency times the orbital separation, and this is the reduced mass, which I called. And the reduced mass divided by the total mass is a dimensionless quantity, and I'll refer to it as eta, although people use different symbols for it. As these guys orbit, they lose energy due to gravitational waves, and we saw from Tom's talk last time that the loss of energy, or the loss of angular momentum, or the loss of period, has relatively simple formulas in the that can be written down in this non-relativistic approximation, even though it's a very relativistic thing that gravitational wave gravitational energy loss is an intrinsic relativistic problem, but you can go very far with this non-relativistic type analysis. Not all the way, but very far. And you get these relatively simple formulas, even if they do have factors of 5 in it. When does this end? Well, the energy is as the energy is lost. Of course, the system inspirals, the period shrinks, the frequency increases in a well-defined way, and it ends eventually when this adiabatic approximation fails, and that'll happen most dramatically when the orbit doesn't close in on itself at all because it's within 1 or 2 cycles of actually falling into a merger. Okay? And you can calculate, and I don't know, has anybody presented a calculation of what the innermost stable circular orbit is so far? Okay, so I'm not prepared with a derivation of it, but in a hand wavy way, I'll just state what it is. It's actually, I even got this wrong. It's three times the Schwarzschild radius of the system. Okay, so it's 6m as opposed to 2m. Does anybody have a question? Okay. So it's 6m, or in units in ordinary units, it's 6 times gm over c squared. Let's see, c squared is a distance. Right, this is units of distance. This is for? This value is for Schwarzschild. That's right. So for Kerr, you will have 2 types of ISCO. You have 2 types of different orbits. So are you accounting for that? Not in this very simple thing. In this very simple thing, let's ignore spin. Okay? It's non-relativistic after all anyway. Okay? I want you to develop intuition on how this goes. So this is actually all you need to calculate a non-spinning in-spiral waveform. And so in my homework, I'm going to ask you to do that. Just calculate the waveform. It's not going to be accurate over many, many wavelengths, but it will be reasonably accurate. Actually, we'll talk about how accurate it is. So I'm going to get. So I would like you to download this problem set. It asks very basic questions. What's the kinetic energy, and so on. And you know all these formulas, but it's helpful to sometimes plug in the numbers and do the numerical analysis. Okay? And if you've never done something like this before, I encourage you to do it. And you can do it actually with 3 different formulas, all of which give equivalent results. Energy loss, angular momentum loss, period loss. They're all expressing the same thing, that gravitational waves are being emitted, carrying away energy and angular momentum, and they all give you the same result. Okay? And you'll make plots that look something like, well, you'll make your own chirp waveform. Okay? That increases, you can't see it here, increases in frequency and increases in amplitude until you better stop it. And you'll stop it at ISCO, the innermost stable circular orbit for non-spinning systems. This is in the time domain. You'll play in the frequency domain as well. It's very valuable to visualize these signals in both time and frequency, or in both with a spectrogram, a time-frequency spectrogram. And I think you've seen time-frequency spectrograms before. I don't have a plot of it here. I should have put one in, so I'll just remind you of what they look like. Here's time, here's frequency. What you usually do is you chop up the data into small bits. You do a fast Fourier transform. We have very fast algorithms for doing it. The fastest one that we use routinely in LIGO is called the fastest Fourier transform in the West, which is just a spaghetti western kind of a reference. You can take a small bit of data, let's say a fraction of a second of data, and Fourier transform it, and you'll find that the signal is dominantly quasi-sinusoidal. Like you only get power at one frequency. And then you step, and as you step, you find that the signal rises in frequency until finally it rises very quickly in frequency. You are approaching merger. Okay? And typically, this is done in linear frequency space through, just your basis set are sinusoids. The Fourier transform is just transforming with a basis set of sinusoids. But we can also do it other ways. We can do wavelet transforms of various kinds, and you'll see examples of those. Okay. So that's a time-frequency spectrogram. Oh yes, depends on the Yeah, it depends on the on what you're looking for. If you're looking for a um, a very transient, short duration signal, then it makes sense to use, well, there's many different kinds of wavelets, but the simplest ones are the standard Gabor wavelets, which are sine Gaussians, which are in quantum mechanics minimal uncertainty waveform packets. Okay, and if you do that, you end up with, and Marianne will talk all about it. You end up with plots, time frequency spectrograms like this one over here. Here's time, 2 seconds. Oh, 2 times 10 to the minus 3 seconds. Oh my gosh. Okay, frequency from 2, 4, 6, 8, 10 times 10 to the fourth. So these are high frequency systems. And you see excess power due to something. I don't even know what this is. To be honest with you, it has, it might be somebody's toy model of a core collapse supernova. Okay, the bounce and the convection and all the various interesting things. Another thing you can do if you're using wavelets like that is you don't have to go linear in frequency. You can go logarithmic in frequency. And we've trained our minds to think in terms of logarithmic frequency, so 10 hertz, 100 hertz, 1,000 hertz, a kilohertz, because it's a neat way of compressing a very large band and visualizing it in a way that we can train our eyeballs. Okay, so yeah, I do have a time frequency spectrogram. So we will see ones like this in which the y-axis here is the frequency in logarithmic spacing, and we call those and which the frequency in which the basis are sine Gaussians, and I'll just remind you of what a sine Gaussian looks like. Here's the Gaussian envelope, and here's a sine wave oscillating inside of it. Let's see, this one has 1, 2, 3 cycles within the Gaussian, so that would be a Q equals 3 sine Gaussian. Otherwise, if there was 1,000 cycles before it damps in either direction, then it would be Q equals 1,000 sine Gaussian. And sine Gaussians are symmetric. Another thing that you can look at is, now I need an eraser. Another basis set that we often use are damped sinusoids. And a damped sinusoid looks similar but different. So start at some point, t equals 0. Exponential goes like this. This is 1, 2, 3, q equals to 3 or 4. I'll remind you, a sine Gaussian, a minimal uncertainty wave packet. What is the Fourier transform of a sine Gaussian? True. True. Correct. But more generally, not just asymptotically, more generally, the Fourier transform of a sine Gaussian is a sine Gaussian. That's one of the special things about it. The Fourier transform of a very narrow sine Gaussian is a very broad one, and vice versa. And vice versa. A narrow, tall one, Fourier transform, is a wide, broad one, not so tall. They are ones in the time domain and ones in the frequency domain. And that's what's so special about minimal uncertainty wave packets in quantum mechanics, for example. But and the nice thing about it is that the turn on of the signal is slow. It turns on and it turns off slowly. A damped sinusoid, what's the Fourier transform of a damped sinusoid? Hex? Rectangle? No. Okay, so because I teach undergraduates all the time, I always like to stress that there is one single most important thing that all physicists must learn. Ooh, what's that? Resonances. The world is full of resonances. They're everywhere. I am a very damped resonance. Okay, a bell is a really good resonance. You ring it up, it rings down. It can ring down very, very slowly. It could have a Q of 1,000,000 or 1,000,000,000, or it can ring down very quickly, very damped. Okay. A damped sinusoid, its Fourier transform is a Lorentzian. A Lorentzian, here's a Gaussian, here's a Lorentzian, longer tails, sharper peak, is a resonance curve. It's the most important curve in physics. Who's going to argue with me? Stefan might argue, because he's been calling these airy curves. They're not airy curves. They're Lorentzians. Or if you're a particle physicist, they're Breit-Wigners. They're everywhere, absolutely everywhere in physics, and they're the stock and trade of engineering. Okay. And I can talk for hours about it, but I won't. But the point is that these guys are another kind of basis, but they have this nasty property that they start abruptly. And if they start abruptly, what's the frequency content here? It's frequency content everywhere, right? Because you take this guy and you narrow it down and it becomes a delta function, and a delta function, its Fourier transform is broad, all frequencies. If you have an abrupt change in a waveform, Fourier transform that, you will have power everywhere. It leaks all over the place. It's called spectral leakage. Well, it's one of the things that that causes spectral leakage are these abrupt changes. You can't allow this. You have to force it to turn on slowly. Okay? Because physically, this is real. Well, there's always some finite time over which you can ring a bell. But there's always some finite time. It's not infinitesimally short. So you have to turn it on slowly or you'll get frequency content at all frequencies. Otherwise, if it's a high Q resonance, you'll get frequency content, well, all over the place, but predominantly in one place. That's called a spectral line. That's how we analyze atomic physics, for example. It's everywhere. Okay, all this is a big fat digression. But we'll be talking more about all these waveforms. Actually, what I want to do is start with another digression, because I just gave you a homework assignment which requires you to do some numerical analysis. And some of you, when you think numerical analysis, you think Mathematica. Okay, you can. It's doable. Okay, but what I want to do is tell you a little bit of the kinds of software and actually give you a whole lot of jargony words that is used in LIGO, in the LIGO scientific collaboration, just for perspective, so you know where we're coming from. Okay, so, I already talked about this and talked about this, and you'll make plots like this using numerical analysis, and I suggest you use Python, because it's just the thing. Everybody likes it. Okay? Okay, so let's talk about the kinds of software that LIGO has used over the years. Until about 10 years ago, most LIGO Virgo collaboration, LVC, data analysis computing was done in C. And most of the code lived in something called LAL suite. LAL is LIGO Algorithm Library, LAL, and suite is a suite of software. Okay, and it's a very, very large suite. Millions of lines of code. Developed over tens of years by tens of people. On the contrary, you heard from Stefan, he likes MATLAB because most instrument scientists use MATLAB. MATLAB costs a lot of money unless you're at an institution where you can get it for free. It's not really a lot of money for the student edition, and the student edition is pretty good, so you can it's like $50 or something like that. But it was ubiquitous in instrument science until relatively recent. The LIGO front end, this is the code that actually controls the detector, both for fast feedback and slow feedback and overall monitoring and control. The front end code is all in C, but it's utterly unreadable C. You develop a model of the detector in MATLAB's Simulink tool, which is an extremely powerful tool for constructing complicated linear time invariant systems of the kind that Peter Solson talked about that are amenable to control. And then somebody pushes a button and it produces a lot of unreadable C code, which runs inside of the many, many computers that control the LIGO and Virgo detectors. The data analysis then is downstream of that. So LAL suite contains many, many subpackages. This one here I'll talk more about that reads in frames, which is how we store the data. LAL simulation produces the waveforms that we're interested in. And there's lots of others. and I'll talk. And LAL inference is where we do our parameter estimation using Bayesian inference, things like Markov chain Monte Carlos. Yeah. Oh, yes, speed. Oh, absolutely. Speed is the one reason. A second reason is that MATLAB is not really, and it's getting better, but it's getting better in some ways and worse in other ways, in terms of being operated at real time. So the LIGO detectors and the Virgo detectors need to be controlled in real time. And there's a clock, a synchronous clock, and it operates at 64 kilohertz, or whatever is the power of 2. That's close to 60, 65 something, 384, something like that. That's the sample rate. So everything is clocked at, what is that, 16 microseconds. There's no way you're going to get MATLAB running in real time at 16 microseconds. Another problem is that we don't have one computer controlling LIGO. We have thousands. You got to take MATLAB and spread it around thousands of computers and have it talk to each other, synchronously. Good luck with that. It's just not optimized for that. Good question. All these code are GNU public license. I don't know if I pronounced that right, and all available to you, so you can download it and go to town. Okay. LIGO data, LIGO and Virgo and Kagra and Geo data are all stored in frame files. Frame files are unique to the gravitational wave community. Nobody else knows what they are or uses them, so that's kind of a problem. We invented them. We felt that we needed to invent something new. We have 3 different kinds of frame files. We have H of T files. That's the strain time series H of T. And these are manageably small. You can download all of the LIGO data. It's gigabytes of data. Okay? Then we have the LIGO detectors don't have just one channel coming out of them, the strain data. The LIGO detectors have 100,000 channels coming out of them. One of them is the strain data. And the other 900 and whatever it is, the rest are all monitoring and are necessary. Okay? Just looking at every aspect of the detector and its physical environment. That includes seismometers and accelerometers and magnetometers and all kinds of monitoring devices that just monitor the environment. Okay? And so that's included. And they are what we call auxiliary data channels. And they're needed to understand the misbehaviors of the detector. They're essential for understanding that. And then we have, and these are on the order of terabytes, and the full raw frames are bigger still. And you're not going to download those. Those are petabytes of data. Okay. All of these, the H of T data are available in the LIGO Open Science Center. LOSC. LIGO Open Science Center, LOSC.ligo.org, which I'll talk more about in a minute. Okay, it includes Virgo data, so we shouldn't be calling it LOSC. So we're thinking, I don't know, gravitational wave open science data. That's GWASC. It's almost as good as GWINC, right? I don't know. What do you think? GWASC. We haven't yet made this decision. Some people hate acronyms, but some people hate typing long words. So we are struggling between GW, Open Science Center, and GW Open Science Center.org. Okay, who likes the first? Who likes the second? Oh, God. All right, well, I don't know. So this is non-trivial. What? Use both. You can use both. Absolutely, you can use both. I'm going to call it GWASP. Marianne likes GWASP. Okay. Now, to analyze this data, we have computers, lots and lots and lots of computers. The LIGO data analysis system, also called the LIGO data grid. LIGO data grid. These aren't equivalent words, but, well, whatever. The difference between them is not important. Is a collection of large high-performance computing. High-throughput computing systems. High throughput computing means lots and lots and lots of CPUs and even GPUs. So for example, the Atlas cluster at AEI in Hanover, Germany has 20,000 cores, on the order of 20,000 cores, and lots of GPUs, hundreds, thousands, I don't know, thousands of GPUs. Okay, so these are big systems, okay? Maybe not, maybe you have something bigger. There's NEMO at the University of Wisconsin in Milwaukee. The Caltech cluster also has tens of thousands of cores. LIGO Hanford, LIGO Livingston, Cardiff has a sizable cluster. Well, left out Syracuse. I guess Syracuse just left the LSC. Huh? Where is it? Kashina. No, God forbid. Somewhere in Italy. Oh, and Nikef. Yeah, so it's growing. It's growing. It's growing except for one thing. When you build, for example, these guys are built a cluster recently in India. It's not available to us yet. I don't know how to use the Virgo cluster. I've never logged onto it. I don't have an account on it. Anyway, unless you're in the LSC, you don't either. So, but hopefully you won't need it unless you're doing some really big number crunching, in which case you got to find yourself a big compute cluster. And these compute clusters are like a user might say, I have a job to do, and it's going to take, I need 1,000 cores, and I need it. So I'm going to take my computing job and chop it up into 1,000 pieces and send it to those 1,000 cores, and usually using some high throughput computing job control language. And we typically use something called Condor, and there's a layer on top of Condor called Pegasus. All these things are either non-mythological or mythological beasts for reasons I can't explain, and they are, job control systems that facilitate you as the user taking over thousands of computers. And if you're really good at doing that, you can even bring the whole damn cluster down, and then you get a badge. And lots of people do that. Okay. Let's see. And these compute clusters have lots of pre-installed software. They have all the strain data and often the reduced data set frames, which are, again, these are gigabytes and these are terabytes. The search pipeline pipelines employ a significant fraction of, for example, the Caltech cluster, but it's not even dominant. CBC is not even dominant. The dominant use of the LIGO data grid clusters for CBC is for CBC parameter estimation. These Markov chain Monte Carlo samplers that explore a large parameter space once we found that needle in the haystack and we want to analyze it to death. And you'll learn much more about that from John Veach next week. Some continuous wave searches are so CPU intensive that they require all the computers in the world and then some. Okay? Literally, there aren't enough computers in the world. So what they like to do is make your computer work for them. So they have this thing called Einstein at Home, which is a screensaver. And you can download it. And it runs on this infrastructure called BOINC, Berkeley Open Infrastructure for Network Computing. And so you got to download BOINC, or maybe it does it for you. And it works on your computer. And when you're not using your computer, it's a screensaver. It turns on, downloads a LIGO data, searches for continuous waves from spinning neutron stars. And if your computer finds such a signal, because so far none of us have, you get a very nice bottle of wine and a ticket to Stockholm. I don't know, maybe we won't win another ticket to Stockholm, but it still would be pretty exciting. So by all means, join in on that, and you can do that in a totally passive way after you've downloaded the thing, and you just run it. It will increase your the electrical bill in your house, I can assure you. It's fun. There are many people, hundreds of thousands, over 500,000 volunteers around the world are running this software. Half of them don't know what it is. They just pay the electrical bill. Okay? And they're all very quirky people. You should try to study all these people and find out who they are. Some of them are aliens. Some of them are pets. There's all kinds of different users. Some of them try to hack the system. and look for signals and find them, and they send it in. And there's only one brute force way to combat that. You send your data to your data chunk to more than one user, and like 3. And then if one person finds a signal and the other 2 don't, you know that that one person is hacking the system. So it's brute force. And as I mentioned, we release data to the public, usually with some delay, through the LIGO Open Science Center. We're still debating about this. It sounds like there isn't a consistent opinion in this room, which is okay. There is a time delay before the data are released. 2 years, by the way, always catch me if I don't refer to data in the plural. There's no such thing as this data. It's always these data or this datum. Little English. The delay is 2 years for 01. It's a year and a half for 02. So we've already released the 01 data. We're still some months away from releasing the 02 data, and we'll probably bring it down to 1 year for 03. And that gives the LIGO scientific collaboration enough time to make all the discoveries, leaving nothing but the dregs for you. Actually, not nothing but the dregs. You guys are much cleverer than the 1,000 people in the LIGO scientific collaboration who've been doing this for entire careers. You're more clever. You'll figure out another way and find a signal that 1,000 smart people working full-time won't find. Thank you very much. That's how science progresses. Okay. Blah, 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 blah. Okay, there's a lot of complexity, of course, to LIGO data analysis. So making the data available to the public is dangerous. Not dangerous. Confusing. There's a lot of things you don't know. Like, you know, we have file indices, we have software that reads the frames, we have data quality information. All of this is hard for us to find, and we make these data. We try to make it simple by repackaging the data. They're repackaged into this format called HDF5, which is used by many places, and even text files. It's all available through the LIGO Open Science Center website, or if you know anything about the CERN virtual machine file system, you can mount this virtual file system onto your computer. Right now, you can do it, and all the LIGO data are there, right there for you. Okay? So it's easy enough if you know how to use it. And there's there's instructions on how to do this on the lost.ligo.org website. We have lots of tutorials. These are Python notebooks. Lots of tutorials to help new users learn how to read in, plot, and understand the data. Much of it is simply signal processing, basic signal processing that electrical engineers know, okay, and that all physicists should know or learn. We had an open data workshop in March. There had tutorials, videos, more Python notebooks, lots of fun things to play with, all available to you, as well as the sensitivity curves that are all available to you, or you can make your own. Here's the LIGO Open Science Center. You can download the O1 data, get started, tutorials, software. The detector status is here. It's about usually with a 1-day latency. In the Open Data web course. Ooh, sorry. Here are just small frame file or small files containing the data for about 4,000 seconds, 4096 seconds. We like powers of 2. Why do we like powers of 2, by the way? Sorry? This beast over here used to run 10 times faster when you run it on a power of 2 amount of data, and much slower if instead of 1024 seconds of data, you gave it 1,000 seconds of data. Now it's about the same. So now it doesn't matter. LIGO and Virgo data. So these are the events. There's 4,000 seconds an hour around each event that we have announced, and more will come. And the entire 01 data release, 5 months of data, and the 02 data will come soon. We downsample it for you to 4 kilohertz. We take data at 16 kilohertz, 16384. This is 4096. We downsample it for you because you may not be because you may not be interested in frequency content above the Nyquist frequency. How many of you don't know what the Nyquist frequency is? Okay. When you are sampling data digitally, for example, a time series digitally, instead of continuously, okay, then you need to sample fast enough to capture all the frequency content. If you have a very high frequency oscillation and you sample like this, you see nothing, right? There's no oscillation there. You got to sample at least twice this. Okay. So your sampling frequency, if it's 4096, is capable of capturing samples per second, or hertz. Then it's capable of capturing frequency content up to half of this. The Nyquist frequency is all, the Nyquist frequency is the sampling frequency divided by 2. Okay? Does that make sense? This is all stuff that was worked out when digital data acquisition first started to appear in the 50s and the 60s. So this is all old digital signal processing fundamentals. Okay, it also, there's information about what data are available when, because the LIGO and Virgo detectors are not always on. In fact, the duty cycle for any one detector is only about, let's say, 2/3. So that is to say, we're on about 2/3 of the time. Sometimes we're down for planned maintenance once a week on Tuesday afternoons, and sometimes due to unplanned things like earthquakes will bring us down for some time. So the duty cycle for a given detector is on the order of 60–70%. Okay? So there's a lot of the time where there are no good data available. And when we require coincidence between detectors, that reduces coincident time to a fraction of that. Okay? And they don't all go down together at the same time always. Planned maintenance, they do. Okay. So the duty cycle for coincidence is on the order of 50%. Okay. So if we run for 5 months, we really only have 2.5 months of data, of coincident data with 2 detectors. The more detectors we have, 2 detector coincidence is a larger fraction. That's one of the reasons why we need more detectors. Right. And let me tell you, if a supernova goes off in our galaxy in that 10%, we are going to be very pissed. Right now, the detectors are all down. No supernovas in our galaxy. Okay? Okay? I said it out loud. All right. Here's one thing I'm not going to say out loud. I am not going to say the word Beetlejuice more than once. I'm not going to say it more than once. If you say it 3 times, it summons it, and I don't want to summon it unless we're up. Okay? That's the only thing that I'm superstitious about. Okay. Here's CERN VM, instructions on how to use this CERN VM file system if you want to use it to get the LIGO data. Here's all kinds of neat Python-based tutorials for learning how to manipulate the data, plot waveforms, calculate signal-to-noise ratios, all kinds of things that you're going to do, okay, in my homework. The Open Data Workshop has tons of good stuff. I encourage you to look at it, and we will look at it maybe on Friday. Noise curves. Kagra, LIGO, Virgo sensitivity curves for a broad range of nearby times, not the far future. If you want the far future, well, the near far future is A+, LIGO A+, which we hope will come online in 5 years. And if you want to go beyond that to Einstein telescope, run GWINC. Okay? With your favorite version of Einstein telescope. Okay, more on LIGO computing. So in contrast to all this C code, most LIGO data analysis these days is done in Python. With the compute-intensive tasks are done in C still, like most of this continuous wave search code is in C. The Fourier transform type stuff that we do, we often do in GPUs, which we code in, GPU version of C, or little snippets of C buried inside of the Python code using this C embedder. The one we're using now is called Weave, but there are others. Some folks prefer to work with R or JavaScript or Mathematica. It depends on the application. But I encourage you to learn how to use Python and Python notebooks if you don't already know. Much light computing can be done with these. And in recent years, there's been an explosion of special purpose code written by all kinds of people who don't follow the dictum, your code must be in Lal suite. In fact, these days, nobody pays attention to that at all. Okay? But instead is kept in often publicly released Git repositories. And Git is a software maintaining kind of a system which versions all your software, keeps track of all the versions you put in. It's a very powerful thing that everybody uses these days, all the time. PyCBC is in a Git repository and it's released publicly. And we'll be talking more about it later. Docker containers are increasingly popular. There are other versions, Singularity. There's a bunch of different kinds of ways of containerizing your software and its environment, like your Python packages, and even the entire operating system can be containerized. You download the container, it lives in your computer in an isolated way. You have a specific environment, specifically, for example, for LIGO data analysis, and it doesn't mess with all your LHC software. Okay? So keep them separate. Otherwise, you'll regret it, I promise you. And this includes, Lal simulation, which has all of our waveform generation code, and Lal inference, which is used for parameter estimation. So you'll be using this, I guess. Here's PyCBC. It's in, I think it's in pycbc.org. And here's a time frequency spectrogram, and here's a chirp. Okay, this happens to be GW5914, I believe. Oh, actually, I'm probably wrong. This is GW170817, which is our one and only BNS event. Here's what a Git repository might look like, or its web base. This one is used for our open data workshop and allows you to download an entire Docker container, 6 gigabytes. It takes a little while to download. That has all the LIGO software you might ever need. And here is the problem set I'm giving you today. It's in here. And you'll be downloading the in-spiral exercise for Les Ouches. The answers are in there as well when you get stuck, which you won't, of course, because these are easy. Okay. In a Python notebook. The answers are in a Python notebook. Okay. Long-winded introduction to software. How much time do I have left? So now I'm going to start talking about our waveforms, because you need to, in order to understand those, in order to understand all the rest of how PyCBC and GST-LAL and these other CBC search codes do their thing. They need these templates. Okay? So I'm going to spend some time talking about the templates. Okay. And you know that the waveforms for compact binary in spiral, merger, and ring down have these 3 parts. They're stitched together, as we will see. We'll use, as you'll see, post-Newtonian expansion for the in spiral. The merger and ring down either comes directly from or is inspired by numerical relativity, which you will hear much more about from Harold Pfeiffer next week. If these are binary neutron star, if these are binary black holes, then you're solving Einstein's equations in a vacuum with no matter at all. Tom showed you how you can do that, at least for semi-quantitatively. And in the end, the only way to solve the 2-body problem in general relativity in the strong field limit is numerically through supercomputers. It's a very, very, very big and difficult calculation. If these are neutron stars, they will be tidally distorted and then torn to bits, tidal disruption. That's complicated nuclear physics. The waveforms for that are not well established. They're still very much under development. And typically they are governed by the, 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 the macroscopic properties of large-scale nuclear matter, in other words, the nuclear equation of state. Okay? So neutron stars, their tidal deformability and disruption, tidal disruption, are governed by the nuclear equation of state. There is no such thing as a neutron star equation of state. Nuclear equation of state. It's a property of the matter that neutron stars are made up of. Okay? And, you know, all neutron stars, we believe, are made up of the same kind of matter. The only difference is how massive it is. The more massive a neutron star is, the more pressure there is and higher density there is in the center, which means you're exploring the nuclear equation of state, which is pressure density versus density, at higher densities. It's the only difference. Yeah? But they all follow the same laws of nuclear physics. The same laws of nuclear physics. They're all in different regimes of density and pressure. And temperature. There's also temperature dependence, and there's also the, you know, how many electrons in neutron matter are available. Okay? So there are parameters that govern it, but the physics is nuclear physics. The same nuclear physics in a regime in which we have never studied it in the laboratory. Got to do it astrophysically. You've all seen these kinds of videos? Who hasn't? Okay, I'll skip it. Oh my gosh. Okay, forget that. I'll show it to you. Okay, so what you're seeing here is a supercomputer simulation. It is not an artist conception. Okay, these two little black dots are the artist part, I guess, because they are showing the two black holes. But actually, they're not. They're a supercomputer simulation. We learned from Eric's lectures that we have to trace geodesics and see how particles near a black hole approach it, and in that way, from future infinity and so on, find the event horizon of the black holes, and those are drawn here. They're computed numerically, very laboriously. The curvature of space-time is shown as colors. Very strong curvature shown in the two-dimensional projection of a three-dimensional world underneath the black holes. We'll see the orbit, and we will see also, maybe if it's shown in this particular version, sometimes it also shows the flow of space and the flow of time around the system, the little arrows and things. And space and time are both falling into these black holes. That is, you take a test particle, and both its position and its clock are changing dramatically around a black hole. Okay, so, and down at the bottom is the gravitational waveform that escapes out to infinity. Now, in here is strong field gravity, highly nonlinear. You cannot distinguish gravitational waves from rapidly changing, highly dynamical curved space-time. You can't distinguish between them. The waves are only identified far away from the source. Okay? So out here, you project out the gravitational waveform out at ideally infinity. They can't go to infinity on a computer, so they do some approximations and some checks to make sure that they're doing it right. And you'll learn much more about this next week. And then as we run this incredible, you know, this thing is going to last a few seconds or something, and it is countless thousands of CPU hours to produce this. Because it really is a numerical solution to Einstein's equation, the two-body problem. Okay? It's all it is, with no matter at all, which is pretty amazing. Okay? I mean, you know, the two-body problem in Newtonian physics was solved long ago, right? What's the solution? It doesn't have to be, but well, I guess you can. Yeah, yeah, that's right for gravity. But really, what I'm fishing for is you solve the two-body problem in general in physics by going to center mass coordinates, and then you've got the system, the two bodies flying ballistically with no forces, and then within the system, it's just the relative motion that matters. Okay? So you just solve the problem by going to the center of mass coordinates. And we go into the center of mass coordinates here too, but you're losing energy. So there's no energy conservation. You're losing energy by emission of gravitational waves. Okay? And it's a very nonlinear problem. And so the two-body problem took many, many years to solve. Okay? It was first solved actually in 1995, down the hall from my office at Caltech by Franz Pretorius, who's now a professor at Princeton. And shortly thereafter, everybody in the world figured out, oh yeah, I can do that. And like all the numerical relativists around the world started solving the problem. It reminded me of, mice don't know how to run mazes. And then you take one mouse somewhere in Australia and teach it how to run a maze, and then all the mice in the whole wide world can run mazes all of a sudden. I don't know how that works. Anyway, that's how it went for solving the two-body problem in general relativity. It's a very, very non-trivial problem until it was solved. Somebody had a question? That's right. This is the Simulating Extreme Spacetimes Consortium, Caltech, MIT, and a bunch of other places. All these postdocs from Caltech and MIT got faculty positions elsewhere. And they are one of the half-dozen leading groups in numerical relativity around the world. Okay? And I'll run it finally after all this stuff. Okay, we're getting a little bit closer. You can see the orbit. You can see the curvature of space-time. You can see the little arrows, which is the flow of space-time into the black holes. They're in spiraling. We're -4 2 seconds. We'll slow down the process now. This is all grossly slowed down anyway, because these things are moving close to the speed of light. Till about right here, where the two black holes merge into one, there's a common event horizon. This is a highly perturbed, newly born black hole. It shakes down, it rings down, and produces this burst of gravitational waves, which goes out into infinity. And that's what produces this waveform that you saw at the bottom. It's a beautiful little thing. Any questions about it? Okay. Okay, I already said this part about the two-body problem. Took decades to solve. Waveforms depend on a long list of parameters, which we're going to talk about. For systems involving neutron stars, there are what we call matter effects, just two words to describe a vast, vast subject. And they're important only in the last fraction of a second before merger. The tidal distortion and tidal disruption happens in a fraction of a second after these guys have been orbiting each other for millions or billions of years. If general relativity is not the correct theory of gravity, in this highly strong field, rapidly changing regime that we are only now beginning to explore, this will be reflected in the observed system. Okay? So that'll be interesting to look for. Okay, so we want to make these templates, we want to understand them, and they're used for many, many different things. Templates are used in a template bank to search for signals, needles in the LIGO haystack of noisy data. They are used not at well, they're called templates, but not in a fixed bank. They're used in Markov chain Monte Carlos, where you step through the high dimensional parameter space of a waveform, generate a waveform, compare it to the data with match filtering, repeat 100 million times, okay, until you find the best match. And not just the best match, but also nearby matches. And that allows you to get not only a best measurement, a maximum likelihood measurement of the mass, for example, of the system, but also the distribution of the posterior probability distribution function of that mass, which is hopefully peaked in the right place. But here's the posterior probability distribution function. It might peak at the right mass, or maybe it's a little off, or maybe it's a little off. But you can say with some confidence, 90% confidence interval, 90% confidence interval, 90% of the probability is between here and here, that the mass lies between here and here. Okay? And you'll learn much more about that from John Veach. They're used for parameter estimation. That's a very big subject now that we have events to estimate the parameters of. They're used for estimating the detector sensitivity, and the detector sensitivity is important. It tells us the volume of space to which we are sensitive, because we're going to assume, for the time being, that the rate of events is proportional to the volume of space. Okay? So the more space, the more events we're going to find. Okay? So the rate is per unit time, number of events per unit time per unit volume. This is surely not true. When the volume gets sufficiently large, you're at cosmological distances. At cosmological distances, you're detecting things from the universe when it was younger. And when it was younger, the rate probably changed. Heck, if nothing else, the rate was time dilated by cosmological effects. If nothing else. But probably, if you go far enough out, if you go out to redshifts of 5 or 10, the universe was a very different place then. At a redshift of 10, that was when the first stars formed. You don't expect to find binary neutron stars when the first stars formed. Okay? Well, maybe you do, because the first stars were big, because they were formed from pure hydrogen gas. You can make really massive stars with pure hydrogen gas. Can't do it with second generation gas, recycled gas, high metallicity. But with primordial gas, you can make high mass stars, 100 solar masses. They live fast, they die young, like a million years, okay? Or hundreds of thousands of years. And they produce black holes and neutron stars. So there were lots of them in the early universe. But at a redshift of 14, there were none. Stars hadn't formed yet. So we know that the rate per unit volume is not so simple when you go out to cosmological distances. It's not a constant. But for the time being, we'll assume it. We need to test our pipelines. We can't just say, I've written a pipeline to find compact binary coalescence. It works. How do you know it works? We run simulations, millions, billions of simulations to cover the parameter space to convince ourselves that we can find these things. We even make small variations in them, because what if GR isn't the correct theory of gravity? We need to test all this. It's very compute intensive. And there are also tools for modeling all kinds of other interesting effects, neutron star matter effects, eccentricity, beyond GR effects, as governed by extra parameters, if you're lucky enough to do that. Okay, there are only, this whole philosophy is that we have parameterized models. Burst searches do not have parameterized models. And totally different approaches are required, as Marianne will tell you. Okay, what are those parameters? Let's start with circular orbits. With circular orbits, there are 15 parameters. Okay. 2 masses, 2 spin vectors. That's 3 numbers, that's 3 numbers. So there's a total of 8 numbers. Okay. These quantities don't depend on the observer. All the rest do. We call these intrinsic, and all these others extrinsic. The intrinsic parameters govern the evolution of the waveform, the phase evolution, which is the thing that we need to get right. They govern the phase evolution. The others simply govern, and except for some subtleties, they govern the amplitude of the signal. Okay? So obviously, the farther away a signal is, the weaker in amplitude. But the waveform itself doesn't change. Except it does because of cosmological effects. If you're out at significant redshift, then the waveform is redshifted between when it was emitted and when you observe it, because the universe is expanded during that time. Okay? So our waveforms are redshifted. As we will see, the phase evolution is governed by the masses and the spins, dominantly the masses. Okay? And if you redshift them, it means that when you extract the masses are redshifted masses. Who has redshifted masses? Who's ever heard of such a thing? Tom has. We have redshifted masses. Okay? We have to correct for that. because we're not interested in the masses as determined by the detector here. We're interested in what those masses really were back then in the early universe. Okay? We want the source masses, not the redshifted masses. That means we have to know the redshift. For binary black holes, you can't just measure a redshift. Okay? We have to estimate the luminosity distance, use the Hubble law, use cosmology to estimate the redshift and the redshifted masses. It becomes almost circular, actually, but it's not. There's the sky location. We usually use, as you'll see later, a natural set of angles for where the sources in the sky is. I'm a detector. Okay? Here's my left arm. Here's my right arm. Okay? This is the zenith. Okay? I care about where a source is relative to my zenith and azimuth, as you'll see why shortly. Okay? It's because of the antenna response pattern of our detectors. But the thing is, that's one detector. There's another detector over here, someplace else on the Earth. Okay? So it does no good necessarily to specify the angles with respect to one detector. You got to specify them with respect to all detectors. Okay? And the easiest way to do that is to specify them with respect to a standard coordinate system, celestial coordinates. The North Pole, South Pole, the first point of Aries, the right ascension, the declination. And don't forget that astronomers use weird angles. They're not physicists. Ooh. Okay? They use all this weird stuff. They don't use luminosity. They use magnitude, whatever the hell that is. They don't use, theta and phi. They use a declination, which is not theta. It's a declination with respect to the equator. Okay? So it's not cosine theta. It's sine declination. Don't ask me. And they don't use angle phi from 0 to 2 pi. They use hour angle from 0 to 24 hours. Well, they're astronomers. Anyway, so we use those two because... look, I'm being facetious. You're absolutely right. Actually, I don't know. Are you really right? Is it really the astronomers who invented the idea of spherical angles? Okay. I'm just being a little bit provocative because I'm at heart a physicist. Because I know too many obnoxious astronomers. Okay. Anyway, another very important angle is, remember we've talked about these orbits being face on or edge on? This is an inclination angle of 0, clockwise. I don't know if I'm getting this right. With respect to you, this is edge on, so this is an inclination angle of pi over 2. And this is face off, counterclockwise. Face on, face off. Face on is clockwise, face off is counterclockwise, or something like that. Okay? And that's pi. Okay? And there's also a polarization angle. If my orbit is not face off, if it's face on and circular, fine, there's no polarization angle. It's right-handed circularly polarized or left-handed circularly polarized. But if it's in between, then it's kind of elliptical, and it could be like this. That's an angle psi of 0, or this. That's an angle psi of 45 degrees, or pi over 4, or whatever, and so on. Okay. Here's a little caveat. As we'll see, if component spins of the black holes are not aligned with the orbital angular momentum L, the orbital plane will precess about the total angular momentum. So the inclination angle is this and not this. And it's changing. And we saw a little cute video of that from Tom yesterday. Okay? That precession is important and interesting, and we'd like to see it for good reasons. The total angular momentum is conserved, right? No, the total angular momentum is not conserved. The gravitational waves are carrying away angular momentum, but it's a tiny effect. It's approximately conserved until the end. There's then the time and phase at coalescence. And what is coalescence? Remember, in this waveform, what part of this waveform, if you can see it here, can you see it? Is the coalescence. I don't even know. I really don't even know. I'm guessing it's somewhere at the peak. So what we do is we assume it's at the peak. And we define the peak to be the coalescence time. But wait a minute. This is a sine wave underneath an envelope. Where's the peak? The peak isn't necessarily here, right? Here's my envelope. Here's my sine wave. I drew it bad. I wanted to draw it such that it happens here. And there's nothing here. Right? There's nothing here. So where's the peak? Well, here's something you can do. As Tom showed us last time, there's two polarizations, H plus and H cross. And the plus polarization is sine-like, let's say, cosine-like, let's say. And the cross polarization is 90 degrees apart. It's sine-like. Okay? And we've got some linear combination of the two. Okay? So what we can do is a mathematical trick that's physically meaningless but mathematically very convenient, which is to combine them. H plus I times H cross gives a complex waveform. There are no complex waveforms in nature. But nonetheless, let's make one. And then this is a sort of a cosine of omega t plus an I times a sine of omega t. Euler's formula, the most important formula in mathematics, e to the I omega t. Okay, plus phi or something like that. The peak of the envelope of the cosine and sine-like parts are the time at coalescence and the phase at coalescence. Does that all make sense? It's mathematical fiction. It's physical fiction and mathematical wonderfulness, because now we don't have to do trigonometry so much. Okay. Complex exponentials are a lot easier than sines and cosines. Yeah? This is the time we want. The highest oscillation in the cosine guy here is here. And the sine guy might be here. Neither of them are sampling this peak. No? Yeah? That's why we want to combine them, so we can find the peak independent of when the highest oscillation is. In this simulation, there's a physical coalescence. That's when those two separate black hole event horizons merge into one. Okay? You got to go down the hallway and ask Harold, when does that happen in your simulation? The waveforms don't tell you. So we try to figure it out. Or if nothing else, even if we don't care when that moment is, we need a fiducial time. And we need that fiducial time to be meaningful here at the Hanford detector, where we're sensitive to plus polarization, and here at the Virgo detector, where we're sensitive to cross polarization, because the time difference is going to tell us the direction in the sky where the signal comes from. So all we need is a fiducial time that's well defined. And we don't care if it's the coalescence time or not. We just need something. And there's no features here. The only feature is something around here. You can't do anything down here. You don't know when the damped sinusoid ends. I mean, it never ends. Yeah.
So you're saying that this peak you use for saying when the merger starts, right? What about the Ringdown phase? How can you determine where the Ringdown phase started and where you start the peak?
Very good question. Probably a half dozen papers in archive in the last year asking themselves that question. Why? Because of echoes. Because of echoes. So there's a lot of people trying to figure out at what point does the waveform fall into the black hole where it can bounce back out again as an echo. Nobody knows the answer to that question, but you can ballpark it. It's got to be somewhere around here. And if it's way over here, you're only seeing a small bit of the ring down. If it's over here, you're seeing parts that don't fall in and echo out. Nobody knows the answer because nobody knows what these echoes are. You'll figure it out. Okay? All right, I'm out of time. I just talked about 15 parameters. You can count them up. Too many. Okay? So we're going to spend some time talking about what these parameters, how we're going to reduce the parameter space to make the problem manageable starting next time. Okay, thanks everyone.